So this is the third and final video of Lecture 3, looking at free body diagrams, and specifically in this lecture, we're going to, in this video, sorry, we're going to look at the three-dimensional questions on free body diagrams. If you're following the lecture PowerPoint, we're starting around slide 23. There's not a lot of extra work here. You've done all the equations before. It's just a case of applying it in 3 dimensions. So rather than having some of the forces in X and some of the forces in Y, we've now also got some of the forces in the Z direction. What that means is you've now got 3 simultaneous equations to solve, which obviously takes a little longer. So it's good to practice your simultaneous equations. The only thing that's contained in this video are the worked solutions for the 2 examples and the group problem solving question from Lecture 3 towards the end. So if you look at the first example, which starts on slide 24, you've got 4 known forces, 1 unknown force, and it's asking for what is force 5, what has it got to be to keep the particle in equilibrium. So very similar to what you've done before, you're just going to write the first 4 forces in terms of ij and k Cartesian vectors, and then find what force 5 would need to be. So I'll attempt to draw the diagram. So there's the approximate diagram. I've left off some of the angles for force 1 and force 4. We've actually got some dimensions that we can use, but if you look at slide 24, you'll see where those directions are coming from. So the first thing we do is we start to write in Cartesian form those 5 forces, or the 4 we know. So force 1, very simple. Force 1 is only acting in the YZ plane, and you can see that in the lecture slides because it's got a grey triangle that's trying to highlight it's only in that one plane. So it's simply going to be, the other thing that's not shown there is the 3, 4, 5 triangle. It's simply going to be 4/5 of 300 J, and it's going to be plus 3/5 of 500 K. So force 1 done, and if you wanted to put that into numbers, you can just put 240 J plus 180 K. Force 2. Force 2, there's no direction, no dimensions given for different directions or different proportions, but if you look, it is actually along the x-axis, and it's in the negative x direction, so it's simply minus 600 I. Force 3, similarly, there's no directions given, however it's in the negative z direction, so it's minus 900 K. Force 4, you'll have to do a little bit more work for, in that you're going to need a position vector, you're going to need the magnitude of that position vector to get your unit vector, and you're going to have to multiply it by the magnitude. So it's going to end up being force 4, the magnitude of force 4 times the position vector divided by magnitude, and if you remember, everything here became a unit vector, so that's the same as saying force 4 times the unit vector of 4. So I'll try and get this on this slide. So position vector of 4, we are given x, y, and z distances in the slide on the in the question. So it is going to be moving 3 meters in the I direction, so 3I, backwards 4 meters in the J direction because it's going along the negative y-axis, and it's moving upwards 6 meters. The magnitude of that is therefore 3 squared plus 4 squared plus 6 squared, all square rooted, with my equals sign, which equals 7.81. So we can then take, we can then get a unit vector of 3 over 7.81 I minus 4 over 7.81 j plus 6 over 7.81 k. And when we multiply 200 by that, the magnitude of force 4 is 200, that's force 4 will then equal 76.8 I minus 102.4 j plus 153.6 k. So now I've got that, I can start to work through. We also know that F5, if I go onto a new sheet, F5, when you look at the diagram, has an X component, it has a negative Y component, the way they've drawn it, and if we assume it's negative to start with, if it comes out as positive, then we just switch the sign around, and it's got a positive Z component. So now we can do our sum of our forces in the X, the Y and the Z. The sum of the forces in the X, we're going to have 76.8 minus 600 plus Fx equals 0. So that's just taking all the I components of all 5 forces, some of them didn't have I components, and adding them together. So we can say Fx equals 523.2. Similarly, the sum of the forces in the Y, we're going to have 240 minus 102.4 plus Fy equals 0. So Fy can be minus 137.6. And finally, the forces in the Z direction, we're going to have 180 minus 900 plus 153.6 plus Fz, and that's all going to equal 0. So Fz is going to equal 566.4. So then to write F5 as a vector, you just take your x, your y and your z. 523.2 I minus 137.6 j plus 566.4 k. And that's the solution to the first example. So example 2, I'll draw it and then I'll talk you through it. So this is example 2. It's exactly the same sort of principle. So you resolve each of the 3 forces in terms of I, j and k, and then you'd work out your unknowns using simultaneous equations. So the first thing we'll do is work through the forces we've got information for. FB is going to be FB sine 30 I plus, put the brackets there, I only have to write it once, that should be a B, so it should be a cos 30 j. We've got that because the FB is only acting in the XY plane. So it's 30 degrees from the y-axis, so you can use that 30 degrees effectively a beta angle. So that will work out at 0.5 FB I plus 0.866 FB J. FC is nice and easy. It's only in the negative x direction, so it's minus FC I. And FD is the slightly longer winded one. It's going to be FD RD over the magnitude, so the position over the magnitude of that position. So our position vector for D will be 1I minus 2j plus 2k. You can get that from the orange labels, but it's clearly shown on slide 28 as well. Then the magnitude of that will just be 1 squared plus 2 squared plus 2 squared, all square rooted, which equals 3. So FD will equal 1/3 of FDI minus 2/3 of FDJ plus 2/3 of FD in the K direction. So now we can form the Fx, Fy and Fz, the sum of the forces in the x, y and z direction, putting together our i's, j's and k's. So the sum of the forces in the x direction is 0.5 Fb minus Fc plus 1/3 Fd, and that equals 0. The sum of my forces in the y direction is 0.866 Fb minus 2/3 of Fd, and that equals 0. And in the z direction we've got 2/3 of Fd minus 600 equals 0. So I can rearrange my final equation, so I can say Fd equals 600 times 3 over 2, which is 900. I can then substitute that back into the next equation up. I can say Fb equals 693. And then substituting both of those into the first equation, Fc will equal 646. So that's the second example from lecture 2, second 3D example from lecture 3, on free-body diagrams. So you pause it now and have a go at the group problem solving activity. One thing to note when you're having a go at the group problem solving activity, again this diagram that's used, it's the 17,500 Newton motor. The diagram that's used has a distance D marked, and you're told in the question that D is 1.2 metres. That would put it in the middle of the plate. So the diagram is not drawn to scale because there is another question which asks you to calculate D with some other information. You haven't got to do that now, but what that means is that your point C in the diagram does appear in the middle of the plate. It appears on the y-axis. So it's not quite as shown in the diagram. Okay, I have attempted to draw this and found that I cannot draw it better than the diagram in the PowerPoint, so I'd look at slide 31 in the lecture notes, or slide 32, to give you an idea of what we're doing here. But the first thing you need is your three forces in Cartesian form. So Fb is going to be the magnitude of Fb. We'll start to see a pattern developing as to how we solve these. How you get from A to B over how far it is from A to B. And we can work that out because we've got all the dimensions we need. So Fb is going to be 1.2i minus 0.9j minus 3k, and that's all of these are going to be divided by the magnitude of those three numbers squared and added and square rooted, 3.354. Similarly, Fc you're moving 0.9 in the j direction, You're not moving in the x direction because, as I said in the previous note, it's actually sat on the y-axis. There's no x component, no I vector. So you've just got those two components. And if I find the magnitude of those, it's over 3.132. Find the FD. You're going to be moving minus 1.2 in the I direction. You're going to be moving 3 meters in the J direction. Sorry, 0.3 meters in the J direction. You're going to be moving down 3 meters in the K. The magnitude of all three of those is 3.245. So now what I can do is I can form my some of the forces in the x, y and z directions. So in the x direction, bringing all my I components together, we're going to have 1.2 over 3.354 FB minus 1.2 over 3.245 FD. In the y direction, we're going to have minus 0.9 over 3.354 FB plus 0.9 over 3.132 FC plus 0.3 over 3.245 FD. And in the z direction, in the z direction, we're going to have minus 3 over 3.354 FB minus 3 over 3.132 FC minus 3 over 3.245 FD plus 17,500 equals 0. So plus because that's acting in the opposite direction. And then rather simply the lecture note just says solve simultaneously to find the answers. If we call this equation 1, 2 and 3, there is a step-by-step guide which is about 2 sides of A4 which I've scanned in and put online. But if I very quickly talk through what happens there, the first thing, we need to cancel out one of our unknowns from equation 2 or 3. So to get the same coefficient, I've chosen to cancel out FC's. To get the same coefficient, I'm going to take equation 2 and I'm going to divide it by 0.9 and then multiply it by 3. And that will give us the same coefficient on our FC. And I'll call that equation 4. And you can see, you can follow this step by step in the scanned in solution online. I'm then going to add equation 3 and equation 4. And I'll call that equation 5. I can also rearrange equation 1. So I'm now going to need 5 and 1. So I'll then substitute equation 1 into equation 5, and it's still all available step by step online. But that will then give me an equation with only FB in it, so I can solve for FB. FB equals 7336.88 newtons. I can then substitute FB into equation 1, and that will give me only FD. I can rearrange and say, well, FD must equal 7,098.44 newtons. I can substitute that and FB into 2 or 3. I chose to do it into 2 in the notes, and that will give me FC to equal 4,567.5 newtons. And then if you want to check it, you can sub it into the other equation which you didn't use in the previous step. So if you found FC using equation 2, substitute all 3 values into equation of 3, and you can check you've got the right answer. But that covers all of the 3D problems on 3 body diagrams, and concludes the videos for lecture 3.